In this video, we will simulate the upward flow of CO2 in a long column with a sidewall that is kept at a constant temperature at each level equal to the geothermal gradient. In the numerical experiment, we used Tuff2 ECO2M to simulate the upward rise of CO2 in a sand-filled long column 500 meters in length. The constant temperature sidewall will be seen to compensate for decompression cooling and serve to maintain relatively constant geothermal gradient temperatures in the system, even though decompression cooling of CO2 is going on. The system is intended to investigate processes occurring during upward leakage, including a transition from supercritical to gaseous pressure and temperature conditions for CO2. The animation results you're seeing here will become clear following the explanation. On the left-hand side of this figure, we show the initial condition by 4 color contour plots of pressure, temperature, CO2 saturation, and CO2 density. On the right-hand side is the same information plotted as a vertical profile of pressure, temperature, CO2 saturation, and CO2 density. From this initial condition, we will simulate the injection of CO2 into the bottom of the column and its upward rise and decompression and related cooling. Results will be shown in terms of the figure here, which has the same 4 vertical columns as shown before on the left-hand side. Now on the right-hand side is a plot of pressure on the y-axis and temperature on the x-axis, and the stability fields of CO2, essentially a phase diagram. The liquid-gas phase boundary, angling upward to the right to the critical point, is shown for reference. The string of symbols represents the pressure and temperature in the column. The lower left-hand end of the string of symbols represents the top of the column, low pressure and temperature, while the upper end of the string of symbols represents the bottom of the column, high pressure and temperature. There's a lot of information in the symbols. The outlined color represents the CO2 liquid, or supercritical saturation. The fill color represents the CO2 gas saturation, and the line connecting the symbols represents the aqueous phase saturation. We will simulate 40 days of upward flow. Watch carefully as decompression cooling related to CO2 transitioning from supercritical to gaseous conditions occurs, for example near the center of the column, while the outer sidewall continues to provide heat to compensate for this cooling. The result is that the temperature stays relatively constant and the CO2 only transitions from supercritical to gaseous conditions without forming liquid CO2, as would happen with an insulated outer sidewall. The action starts at the bottom of the column, the top of the string of symbols, as CO2 enters the column and rises upwards and cools. The progressive rise of the CO2 can be seen in the left-hand side contour plot of CO2 saturation and in the right-hand side phase diagram by the symbol colors, indicating supercritical CO2 low in the system and then transitioning to gas. The gaseous CO2 never cools enough to reach the liquid-gas phase boundary. It appears the constant temperature sidewall can provide heat to the system to compensate for decompression cooling. The significance of this simulation is that for upward flow in narrow channels like wells or fault zones, heat flow from surrounding rock may be able to prevent the formation of liquid CO2. In these cases, decompression cooling cannot play itself out very far, and the upward rise of CO2 would not be hindered by three-phase relative permeability or increased viscosity associated with liquid CO2. This is in contrast to the case of the insulated outer sidewall, in which decompression cooling is strong enough to cause liquid CO2 to form. For more details and simulation results, please see our paper cited here, and please remember to look at the supplementary material where you'll find links to YouTube videos of the animations.